Thank you, Pat. That was a very generous introduction there, and I appreciate that. And I've known Pat for a number of years, long before the Iowa Power Fund Board. We served on the iRenew board together. And I remember coming into this unique building and meeting upstairs in one of the laboratories, and we all thought it was so cool. This green building here, way ahead of its time. And so it's been my pleasure to work with Pat for a number of years. I am an electrical engineer, work in the power field, work with a lot of wind generation projects, but over the last 2 years, I've become really enamored with the issue of low energy nuclear reactions, LENR. And a low energy nuclear reaction is also been known as cold fusion. And this evening, I want to talk about this subject, and I'm going to attempt to answer these questions. What is LENR? Whatever happened to cold fusion? Well, how does this stuff work? How does it compare to nuclear energy sources? What companies are working on this technology today? How will this technology be used? And how much will this technology cost? That's a very important one. And can I purchase an LENR or Lenr product today? And how will it affect the natural gas and electric utility industries? That's an area that I work with. And then I'll conclude with a few thoughts of my own. So, what is low energy nuclear reaction? Well, LENR, and I'll call it Lenr, or LENR tonight, it's been called many different terms, and the one that I like the best is low energy nuclear reaction. But there's another term, another definition of LENR, that's lattice-enabled nuclear reactions. And then there's another one called the Leclerc effect nuclear reactions. And then there's a LANR, Lenr, lattice-assisted nuclear reactions. And then we have the CANR, chemical-assisted nuclear reactions. And then the CNT, cold nuclear transmutations, metal deuterium energy, Fleischmann-Pons effect, anomalous heat effect, the catalyst-induced hydrino transition, the deuterium permeation-induced transmutation, what Mitsubishi Heavy Industries out of Japan likes that term, and the Rossi effect, and the CECR, which is one controlled energy capture reaction, and the HENI, heat energy from nano, whatever. So many different names. What's that tell you? Well, that tells you the industry's not quite settled yet. There's a lot of research going on, and they're learning new things. But the most famous of all of those is called cold fusion. And in general, this is a definition by one of the Edmund Storms, who is an author of one of the books I have here, is a nuclear process initiated on rare occasions in apparently ordinary material without application of significant energy that generates heat in nuclear products without expected radiation, when any isotope of hydrogen is present. Or I'm going to make that simpler. In essence, hydrogen atoms are fused into helium atoms inside a metal lattice structure, and other element transmutations may occur. That's my simpleton way of describing it. So there's been a lot of terms for it. Well, last July, I went to the International Conference on Condensed Matter Nuclear Fusion, ICCF. It really stood for International Conference on Cold Fusion. And it was down in Columbia, Missouri. And the majority of the Lenr research scientists attend this conference, and it's held every year or every other year. There were 215 attendees from 21 countries. There's the group of candidates. And you'll see me here as the guy trying to look smart in this group of otherwise overachievers. There's so much, experts, and a lot of these people have advanced degrees, a lot of doctorate degrees, and some of the most brilliant people I've ever seen, met in my lifetime are in that group photo. It was a hot day down there, and we were breaking out in sweat as they were taking that picture. But I also attended a one-day pre-conference on Lenr with 25 other neophytes. So I was down there for 5 days in Columbia, Missouri, learning about Lenr and cold fusion. And while we were down there, we toured the Nuclear Institute. It was a new institute, one of the first ones in the United States, that was designed to study this concept, this low-energy nuclear reactions. It was a donation, a $5.5 million donation, and they set this lab up right on the university campus, and we toured the lab. And when we were in the lab, we saw all types of equipment, and there was cold fusion happening while we were touring the lab. We were in its presence, feet away from where it was occurring. And I got to know one of the attendees who was at the conference, and he works for Stat Oil. How many of you have heard of Stat Oil before? It's the 11th largest oil company in the world, and of all companies in the world, it's the 26th largest company of all types of companies in the world. What are they doing there? So I asked Jostein, why are you here? You know, I was expecting some clandestine motive, like, oh, we're going to try to diffuse this and railroad this off and prevent this from ever happening. But no, instead he says, this is great. This is the kind of energy source that our company was looking for. We need this, so everybody needs this. So he was one of 23,000 employees at Stat Oil. He was one of them there that was attending this and following with much interest. So the energy industry is really interested in this too. So before we get into my discussion today, we're going to have a little refresher on nuclear physics, and I took one class that had a few sessions on it. So as you know, chemical reactions, such as the combustion of natural gas, they just change the composition of chemicals. They don't change the actual elements. But a nuclear reaction is where you have one element and something happens and you create two different elements. So, and it usually has a different number of neutrons in the nucleus. And I know some of you shudder when you see the periodic table, but here's the old periodic table. And for example, one of the elements that is used a lot here is nickel. And it's got 28 protons in the nucleus and typically about that many neutrons also. If this changes into a different element like copper, then it's a nuclear incident. It's a nuclear reaction. When an element changes into a different element, then that's a nuclear reaction. Now, a fission reactor, like we have at Cedar Rapids, takes an element and it splits it into other elements. It takes uranium-235, and when it splits, it goes into a whole range of other elements. And I don't recall how many different elements come out of actually a fission reactor, but it's dozens and dozens and dozens with various isotopes. And a fusion reactor does the opposite. It takes two light elements, typically hydrogen, and fuses them into a larger element. And the sun is a perfect example of a fusion reactor. And I don't recall exactly the fusion reaction that's going on in the sun, but I don't believe it's hydrogen, but it's a heavier element. And the problem with attaining fusion here on Earth is called the Coulomb force. You know, you have protons in the nucleus, and you try to get those nucleuses too close together, and the protons repel each other, the Coulomb force. And it's very hard to get the protons and nucleus combined in together. And so that's the main challenge here on Earth. On the sun, high pressure, high temperature, you can do that. So to overcome this Coulomb barrier, you have to slam together the atoms with either high kinetic energy, and most fusion experiments use clouds of ions and strong magnetic forces. It's easiest to fuse just hydrogen because those are the smallest atoms, and they're the easiest to fuse together. So most hydrogen has one proton and no neutrons. That's called protium, or hydrogen, just regular, we call it hydrogen. Deuterium has mass of 2, a proton and a neutron in the nucleus, and tritium has 1 proton and 3 neutrons. So hydrogen, protium, deuterium, and tritium, and most of the water contains just hydrogen or protium. So light water now, light water is water that has just one proton in each of the two hydrogen molecules. So H2O has got two hydrogen atoms, and each of them have just no neutrons and one proton. And then semi-heavy water has one of the hydrogens is deuterium and one of them is protium. And then heavy water, the true heavy water, is both hydrogen atoms have deuteriums. So this, I'll be throwing around the words deuterium here a couple times this evening, so that just gives you an idea. Deuterium is just one of, it occurs in nature. It's probably like 1 out of every 6,000 molecules of hydrogen is a deuterium. Well, the initial discovery of Lenr was, or cold fusion, was it's a reaction that creates unexplained or anomalous heat. And it was first discovered by two electrochemist researchers, Martin Fleischmann and Stanley Pons. And Martin Fleischmann was one of the world's top electrochemists. He was known throughout the world. And Stanley Pons headed up the University of Utah's chemistry department. And he co-wrote more than 200 scientific papers. These guys were not slough-offs. Brilliant, brilliant people. Here they are in their laboratory. And they started working, they got interested in this because of work done in 1926 by German researchers. They were looking at palladium, which is a metal, a heavy metal like platinum or gold, and heavy water. And these two researchers back in 1926 said, hey, something strange is going on when we put this in an electrochemical cell. They just said, we're getting extra heat out of this, we don't know why, we don't have time to work on it, and so they let it go. And so there was some additional, a little bit of additional work was happening, but a palladium cathode is, palladium is just like a piece of metal, and if this were palladium, it would cost me about $400. This is a piece of tin foil. You can pretend it's palladium. But you put this down in an electrocatalytic cell, which is just, it could be a jar. If you've been in chemistry classes, you've had these before. And you put an anode and cathode in there and apply electric current between the two. And then you put some water solution, an electrolyte in there, and you have an electrocatalytic cell. Well, palladium is one metal that hydrogen can be absorbed right into the metal. Hydrogen is a small molecule, it can go right into the metal. It's hard to believe, but hydrogen gets absorbed into palladium. And so it's used for a lot of experiments. So here is the cell that Fleischmann and Pons used when they announced their cold fusion. And so they've been working on this for quite a while, for a few years. And in 1985, they were running this experiment with this electrolytic cell. And their piece of palladium was a a little cube of palladium that was a centimeter by centimeter. And they've been running it for months and months, and they couldn't get anything to happen, so they turned up the current a little bit, up to over an amp or so in the cell, and they went home for the weekend. And they came back on Monday morning, and they said, hey, where'd our experiment go? When they went into their laboratory. And here was their lab desk, and there was a hole right in the middle of where their lab was, their equipment was, as a 1-foot diameter hole in a lab table. And then if you look down below that, there was a 4-inch hole in the concrete. It didn't go all the way through, just 4-inch hole or so. And they were a little sheepish, and there was this dust all over the place, you know, from this concrete being burned away or whatever. And they smiled at each other, and they just knew they had finally figured it out. So that was the start. So 1985. And so they kept working at it. And instead of using blocks of palladium, they used foil and wires, palladium from that point on, so they didn't have that problem. And so after putting a lot of their own money into it, about $100,000, they finally said, went to the university and said, hey, we've got this process. And the University of Utah was fascinated, and all they could think about is making money on a patent, fusion. So they had a conference, a special news conference, announced it, and it made news all over the world. How many of you are old enough to remember the announcement of cold fusion? It was neat. It was a neat time. And there is a cover of Time magazine back in May of 1989, and how two obscure chemists stirred excitement and outrage in the scientific world. So they became celebrities. They went to the House Congressional Committee, Science Committee, and they testified there. And there they are, they're telling about their experiment. So everything looked great. So let me tell you what the experiment was. It was, just like I said, it was an electrolytic cell with a palladium wire, is the one that they held up at the news conference, and they put a constant current power supply in it, and they forced current into one electrode and out the other. And on the electrode where the hydrogen from the water is being expressed, little hydrogen bubbles, there's an intense concentration of hydrogen right on the surface of that palladium. And as a result, a lot of that hydrogen goes into that palladium metal. And so you've loaded up the metal with palladium with the hydrogen. And here's a picture of the cell. And if you've been in a chemistry class, it's not too different. There's a temperature measuring equipment in here. And they also are very careful to measure the heat produced by the cells. So it was a very well-designed cell. And these guys were experts. But it took years of experimentation to get this excess heat. I mean, they get it occasionally, and it was fickle. And for example, a cell might be operated for a month or two under varying conditions. They'd vary all types of things. And then they finally get it produced, and then every once in a while, they get a blip of excess heat. And so they published a paper. And in this paper is a graph in here. And this graph is so famous now, it's on a t-shirt. And you see that graph there, and that is a graph of temperature over time, the time across the bottom axis. And you see this gradual increase in temperature. It has nothing to do with cold fusion. And then you see that blip there, that increase. And I believe that occurred, I can't remember, that's like a 1 watt amount of heat there for, I don't know, it was a day or something like that, or part of a day. And that was big news. It's hard to measure 1 watt in a cell like that. But that's what caught the world's attention, being able to produce that. So they got better at replicating this, but it still wasn't, they didn't understand what was going on. They had no idea what the physics were behind it. And after the announcement, well, scientists around the world rushed home to their laboratories and said, well, let's do this. But it was different because the University of Utah was involved. And the patent office in their university said, wait. Don't give out the details about doing this. Don't tell them everything because we want to get our patent first and then you can tell them. That's not the way the scientific community really typically works. Everybody shares their stuff, there's a lot of peer collaboration, and you go back and forth and you do this. Didn't happen. And as a result, it took them years and years to get results. Just think what happens when the whole world rushes out to do it. Hardly anybody got results. They had the same problem that Fleischmann and Pons did. So what did the world think? The world thought that these guys were trying to pull something off. So nobody was able to duplicate it, and then the prominent members of the scientific community, including MIT, came down hard on them, and Fleischmann and Pons' reputations were ruined. It was just one of the most ugly things in the scientific world to see well-respected scientists, just a reputation ruined just so quickly. So it was very sad. So as a result after that, it was written off. And it kind of reminds me of the Wright brothers flight. It was a 59-second flight in 1903. It wasn't practical. And Thomas Edison's light bulb, which lasted 13 hours, it wasn't practical either. And neither was Fleischmann and Pons' experience. A few watts of heat, so what? Who cares? However, both of them changed the world, and especially this one is going to have just as big an impact as the other two. So most scientists and research institutions saw what happened to those two poor scientists, and they said, I don't want any part of this. And they steered away from researching it. But there was a few individuals around the world and a few companies. One of them is Toyota Company, Toyota Motor Corporation, where they continued on research at a very low level, key level, typically out of the limelight. And some of them had to disguise their research. They have very limited funding. Sometimes scientists use money out of their own pockets to do the research. But a few key individuals kept working in this area. And Fleischmann and Pons helped them as best they could. And then they started having conferences. I believe in 1990 was the first conference, a year after it was first announced. And there weren't many people that came to the conference. But since that time, the good thing about this is that all of the research has been published. There have been 1,700 papers written on this topic. And if you look at the title of the papers, and I've got a list of 1,700, they're on your website, I believe, Frank, and you can't even hardly understand what they are, and nowhere do you see the word cold fusion in it. You see all these other things that are necessary discoveries for trying to figure out what's going on. So there was very slow progress due to extremely limited funding. But over time, more and more researchers were able to produce a little bit of excess heat. And so as of today, there's at least 170 labs or institutions around the world that have replicated these results, that have found excess heat that cannot be explained by anything else. Nothing else can explain this other than a nuclear reaction. And, believe it or not, the Ames laboratory right here in our state of Iowa in 2009 published a paper where they too had found some excess heat. And they found a ½ watt to 3 watts. Half a watt. You know what a ½ watt is? It's not much energy. So people weren't really excited about this new energy source being only a ½ watt anyway. So, but there's been demonstrations of Lenr around the world. And most of the research up to about 2010, they had been getting excess power of about 1 watt to 26 watts. Well, what's 26 watts? Well, that's not hardly enough to, it's not enough to light an incandescent light bulb anymore. So people said, well, how important is this? And oftentimes this research here's an engineer working on a little electrochemical cell there. And, not too exciting. But over time, the power level had kept going up and up, the amount of power that they were able to get. And then finally, about 2011, the power level shot up. And in 2011, a new person came on the scene, and his name was Andrea Rossi. He had a different approach. And he got, this time, thousands of watts. Thousands of watts.